All right. Hi, everyone. My name is KevinGima, and I'm studying excited state dynamics in one-dimensional thermoelectric materials. Uh, okay, so before I get started, I need to lay out some quick background information, which is what is a charge transfer? Why is it important? Okay. So here, right here, you have a couple of electrons, and here you have an electron hole. So you see lights, and it's exciting this electron, and then this electron breaks free and travels to this hole. So then after the electron transfer, this electron hole is filled. So charge transfer is simply the movements of electrons. Now, why is charge transfer important? One reason why it's important is because it has a lot of uses in the semiconductor industry. All right. So semiconductors are used in everyday things from cars to microwaves to everything else. So improving the charge transfer and the charge transfer rates within those semiconductor devices will definitely improve their efficiency. And furthermore, charge transfer helps us to study non-adiabatic dynamics. Let me explain what regular adiabatic dynamics is. So, in the regular adiabatic approach, you have your nucleus or your nuclear states, and then your electron, which has your electronic states associated with it. In the regular adiabatic approach, we're assuming that the nucleus doesn't vibrate or move at all, so it doesn't move with respect to time. So because it doesn't move with respect to time, the orbitals associated with the electron doesn't change. So therefore, the expectation values of, like, for instance, energy, momentum, and everything else doesn't change with time. They stay with constant. So that's the regular adiabatic approach. Uh, Now, this is in contrast with non-adiabatic dynamics. In non-adiabatic dynamics, we're assuming that the nucleus position changes with time, it vibrates. So when it vibrates, the orbitals associated with the electron change, and when that happens, all those position expectation values I mentioned earlier, they also change in time. All right. So non-adiabatic dynamics comes into play when we're studying charge transfer. Okay, so I studied the thermoelectric effect, but before I get into that, I need to make a quick contrast with the full photovoltaic uh, effect. So the photovoltaic effect is simply when light shines on an electron and that electron gets excited. So if you look at the schematic I have here, you have sunlight. It shines out on this solar panel. Uh, you have your N types here, which is associated with the electrons, and your P types, which is associated with the electron hole, and you have your junction between the N and P types. All right. So when light shines, it excites the electron. Electrons move, and that it induces a current. So as you see here, uh, this whole solar panel and the photovoltaic effect is being used to light this light bulb right here. So that's a quick example of the photovoltaic effect. All right, and this is in contrast to the thermoelectric effect, which is what I'm studying. Excuse me. So you have here in panel A a hot side and a cold side. Now, initially, all the electrons are right here on the hot side. So here on the hot side, you have some electrons that have more kinetic energy than other electrons. So the electrons with more kinetic energy uh, go here to the cold side, and then when enough of them gather on this end, they repel the electrons that have stayed behind on the hot side. So you have electrons on the cold side right here and the hot side right here. So because you have two electrons uh, on both sides, they induce a voltage between them, and then that can be used to power a current. So panel A is the thermoelectric effect, and then panel B uh, shows the whole thermoelectric apparatus, and that's being used to power an electric circuit with the resistor right here. So this whole thermoelectric apparatus is supplying a voltage. Okay, so now that I got the background information out of the way, I can talk about what specifically I'm studying, which is lead telluride nanowires. So I'm studying lead telluride nanowires. Now, some of you might be thinking, um, we can use lead telluride thin films. Why don't we use them? Uh, Simply because researchers have found that with nanowires, they're easier to modify, monitor, and control. So, for instance, if you wanted to modify the electronic structure or the atomic structure, which is specifically takes some atoms out and put new ones in. I'll get into more detail on that shortly. It's easier to do that with nanowires than films. All right, and these nanowires have been widely researched as a potential thermoelectric material. So over the past 5-10 years, a lot of researchers have looked into lead telluride and nanowires, and they show a great promise as a potential thermoelectric material to be used in semiconductors. Just to give you a quick example why, you have the conventional band gap for our current semiconductors. They're around 1.5 electron volts. But however, the PBTE band gap, PBT is lead telluride. The band gap is around 0.32 electron volts at 300 Kelvin. So that is a big difference. The band gap is smaller, and that's a really good thing. So that's one of the main reasons why lead telluride nanowires are being looked at. However, many challenges remain in studying these things. Um, doping any material. Wait, I should back up by saying that even though there's a lot of potential with these lead telluride nanowires, um, I'm sorry, does someone have a question? Okay, I'll keep going. I thought someone had a question.
Can you explain what is conventional band gap?
I'm sorry, can you say that again?
What is conventional band gap?
That's simply the band gap of the regular semiconductors we have today. So so the conventional band gap range I've shown here is what a typical semiconductor will have. And by contrast, the band gap of lead telluride is only 0.32, 0.33 it, electron volts. So because it has a shorter band gap than your average uh, semiconductor, it has a lot of potential to be used in semiconductor devices. Does that answer your question?
Yes, I mean, we can get back to this later, but please go ahead.
Okay.
Yeah.
All right. So any challenges remain simply, even though there's a lot of potential, researchers have found it very difficult to actually apply lead telluride nanowires to typical semiconductor applications. Um, this is because there's a lot of challenges in the design process of these uh, nanowires. Um, one one thing researchers are looking at to improve the efficiency of a charge transfer in lead telluride is doping. Doping any material modifies its electronic properties. So the reason we're looking at doped lead telluride and nanowires in comparison to undoped lead telluride nanowires is research in the past have found that doped lead telluride nanowires have a increased charge transfer rates, have better charge transfer rates as opposed to undoped lead telluride nanowires. So that's the reason I'm also looking at lead telluride nanowires. I mean, doped telluride nanowires. So I need to go into the specifics of the doping process of how it occurs. Here on panel A, you have a regular undoped nanowire. So its valence band and conduction band remain unchanged. In panel B, you have sodium doping. So what's happening here is the valence band is empty. Is empty. One shell of it is empty, and then in iodine doping, one shell in the conduction band is filled. So out on panel D, we're putting sodium and iodine doping together. Well, what's happening here is that due to sodium doping, the valence band is empty, and then the electron from here transfer goes to the iodine, all right, and the conduction band of the iodine is filled, all right. So if we remember from the periodic table, sodium has one extra electron and one valence electron, and iodine needs an extra valence electron to complete its shell. So what's happening here is that sodium, the donor, is is donating its electron to iodine, the recipient, so it can fill its outer shell. So this is the doping process in a nutshell. Okay, and then here's a model of my doped nanowire. This is my lead telluride nanowire. These pink dots right here are my iodine dopants right here, and these blue dots right here are my sodium dopants. All right, and this region is my n-doped p doped region. All right, and the length of the nanowire I'm looking at is around 110 angstroms. It has a cubic structure. It has approximately 300 atoms. Um, there's a 1-to-1 ratio between my lead and telluride. All right, and if you look at this chemical equation right here at the bottom, lead has two extra electrons in its outer shell. Telluride needs two extra electrons to complete its outer shell. So lead donates is its two extra electrons to telluride, and together they form a compound. All right. So important thing to note is that sodium replaces lead because they both have extra electrons in their outer shell, and then these these iodine dopants right here, they replace the telluride because they both need electrons to complete its outer shell. All right, so that's a quick recap of the structure of my nanowire. Okay, now let's take a look at my methods. Um, well, the first thing I did was I used density functional show theory right here. For those who don't know what density functional theory is, we all know in quantum mechanics, we use the wave function, um, and we multiply that by the wave functions on complex conjugate, and we square, we get our probability density. Well, instead of using the wave function to compute expectation values, we're using charge density. That's this row right here. All right. So this charge density is computing did by multiplying the wave function by its complex conjugate right here. This times that gives us our probability density, and we're summing across all of our occupied orbitals from 1 to our HOMO, which is our highest occupied molecular orbital. So I use density function theory coupled with my software to find the energy and uh, position expectation values, which I'll talk about more later. And then a quick note, the I got the positions of the ions from Newton's equations, classical mechanics, aka molecular dynamics. I just wanted to make a quick note about that. And then, so I got my expectation values from density functional theory, and then I use non-adiabatic couplings right here to see how my energy and position expectation values uh, change in time. So I'll get to go into those results shortly. All right, and then right here, this is what I use to compute my transition rates, uh, which is it, which is essentially how the rate at which my electron is jumping from orbital to orbital. So this is how I'm computing my transition rates. I just wanted to point out very quickly that this is analogous to Fermi's golden rule right here. So this is proportional to the charge density right here. So this rate is proportional to the charge density. Just wanted to quickly point that out. And then the last thing I have here is my density matrix. So I'm looking at how my density changes with time. Um, a quick thing to point out here, the density I have here for my density matrix dynamics is time dependent. The charge density when I'm looking here at density functional theory is not time dependent at all. So this isn't time dependent. This is just a quick thing I wanted to you guys to keep in mind. So this is what I use to see how my charge density is changing with time. This is I use the commutator between my Hamiltonian and my time dependent charge density, and I added this to my transition rates. This is equal to that times my time-dependent charge density. And I use this to find how my expectation values of position and, and energy are changing with time. All right, so the next thing I have here are my observables. So I calculate, so from my expectation values of my electron and my electron hole energy, I use these to get my ele electron relaxation rates and my whole relaxation rates. So to find out how both of my energy expectation values are changing with time, I multiply the charge density associated with each orbital by each orbital's energy, and then I'm adding it across orbit each orbital right here. All right, and then a quick thing to note is that if I sum up the charge densities for each and every orbital, they come out to one. So so charge density in this case is analogous to our wave function. When you take the amplitude of the wave function, you square it, you get your probability density, and then if you integrate the wave function squared across all time and space, you get one. It's the same thing right here. All right. So next we get my rates of relaxation, so my electron relaxation rates and my whole relaxation rates. So these relaxation rates are equal to the derivative of my uh, my electron energy with respect to time and my electron hole bit with respect to time. So even though this is the way, this is technically what's used in practice, my MATLAB code used this integral form right here. So the integral form of these guys is what I used in MATLAB to find my relaxation uh, rates right here. So I'm integrating across all time from 0 to infinity right here. I'm using that to compute my electron relaxation rates and my whole relaxation rates. All right, next slide. Okay, and I just wanted to very quickly point out the band gap law. So one of the primary goals of my research is I want to see how well my relaxation rates for my electron and my electron hole will follow this band gap law. Um, my relaxation rate is equal to a constant times e to the negative alpha delta E. Delta E is the change in energy. Alpha is 1 over the Boltzmann constant times temperature, and this is the electron relaxation rate. So as stated, one of the primary goals of my research is to see how my relaxation rates follow this band gap law. Okay, um, so now for my results, the first thing I have here is my density of states. So right here is my doped nanowire, and here is my undoped nanowire, valence band, conduction band, valence band, conduction band. One thing I have to point out is that I'm not positive that the widths for these two graphs are equal. So when I review the research I have so far, I have to redo these, make sure that the widths for these two graphs are equal, so that these density of states can be compared properly. And I just wanted to very quickly note that the band gap states come from the buildings.
All right.
And then right here is my absorption spectra. Right here, here is my uh, undoped nanowire. Excuse me, right here. And then on my right hand side is the absorption spectra for my doped nanowire. I just wanted to point out that this transition number one, which is right here, is dark. This is essentially congruent with the expected results since the electron is transitioning to a higher energy orbital right here. Uh, these absorbed photons for this transition right here show up as a dark transition because the photons of these wavelengths have been absorbed. Okay, so I just wanted to excuse me, I just wanted to very quickly point this out right here. Okay, and here is my fluctuation graph, or in other words, how the energy of my constant orbitals change as a function of time. So I took this when the temperature was 1,000 Kelvin. All right, here we have my conduction band and valence band, and where my mouse is hovering, that is essentially the band gap. All right. Now an interesting thing happened. So look at here. You have your band gap at time equals 0. However, as time goes onward, this band gap gradually closes until it essentially becomes 0. All right. Um, okay, so we know that the position of your nucleus changes with time, so it's dependent on time, and we know that the energy of each orbital right here is dependent on the position of the nucleus. So by applying the chain rule, we know that the energy is dependent on the nucleus's position. All right. So that's why we see here that the band gap is changing with time. All right. So that the next thing we have here is my red field tensors. So when I was talking about transition rates in the methods sections, I got these results right here, with which shows the transition rate for each orbital transition. So you have orbitals on the x and y axis right here, and then on the z axis is a transition rate. So it's the transition rate for an electron going from orbital I right here to orbital J here. All right. So the first thing we notice is that the graphs here show a positive correlation between the temperature and transition rate. If we look here at the 300 Kelvin graph, um, we see here that the transition rates uh, for uh, for orbitals near the HOMO and LUMO are close to 0, or they're not as high as the outliers here from the HOMO and LUMO. However, we see that as the temperature increases, so 300, 500, 700, 900, 1100, we see here that this gap gradually closes until uh, there's no band gap there whatsoever. So this agrees with what my previous graph shows. Okay, next slide. So these are the orbitals I've looked at in my research. So very quickly, I want to point out that my whole orbitals are localized near my sodium dopants right here. All right, and then my electron orbitals are uh, are localized near my iodine dopants. So that's one thing you should notice very quickly. Okay, and then here is my waterfall graph. Here is how my probability density change, how it changes with energy and atomic distance. So here we have my conduction band and my valence band, and I calculated my probability density with this equation right here. So it's simply taking my wave function squared and then integrating it over all space will give me my probability density right here, or in other words, my charge density. Okay, the next thing uh, I'm gonna get to is my charge density distribution, specifically um, how they change with energy. All right. If you look at my 300 Kelvin graphs right here, they're essentially horizontal lines. So you see no change with respect to time. The energy just remains constant. However, as the temperature increases, um, you see that the energy changes with time, and it even starts to change faster. One thing I want to very quickly point out is that there might be some error with my 500 and 700 Kelvin graphs. So the energy differences between my electron and my electron hole for 500 and 700 are unexpected. So I need to do more research and to find out whether these results for these two temperatures are due to human error or whether they are legitimate findings. Okay, now in this figure right here, we're seeing how my charge density distributions are changing with position. All right, so one thing you see here is that sorry, all my charge transfer is localized near my iodine dopants. So you have my sodium dopants right here, iodine dopants right here, and you see for all of my graphs, all my transitions, that the charge transfer is localized near the iodine dopants. Um, this is in line with our expected results, since an electron is uh, since our sodium atom is acting as our donor and our iodine atom is acting as our recipient, the charge transfer should go towards the iodine. The electron should be moving towards the iodine. So that's in line with our expected results. Also, if you look at these graphs, the magnitude of the charge transfer increases with temperature. So if you look at these 300 Kelvin graphs right here, you see little charge transfer. By the way, the dash line is my electron, and the solid line is my electron holes. I forgot to make that clear. So as I was saying, for my 300 Kelvin, there's very little charge transfer. However, as the temperature increases, the magnitude of that charge transfer increases. So I very quickly wanted to point out that qualitative observation. Okay, and finally, I'm studying how my uh, relaxation rates are changing with my energy. So relaxation rates for my electron and my electron hole, and I've seen how they're changing with energy. All right. Well, one thing I see here is that the band gap law, which is what I showed you guys earlier, uh, they seem to be only applied to electrons with higher temperatures. So you see here that the 700, 900, 1100 Kelvin graphs here, they seem to follow the band gap law perfectly. However, the 300 and 500 Kelvin graphs right here, they show a very limited correlation with the band gap law. And the relaxation rates for my electron hole, um, they they don't really appear to follow the band gap law at all. So I'm going to say that the band gap law has a very limited applicability to my 8 electron holes. All right, and then the last result I have for you guys is I want to see how my relaxation rates change with temperature. All right. So if you look at my graphs, one thing you'll notice almost immediately is that these graphs overlap each other. All right. So what this essentially means is that the rate, excuse me, the rate at which my relaxation rates change with temperature is independent of no, or of my orbital transitions. So no matter what orbital transition you're looking at, the rate of change for my relaxation rate with respect to temperature is going to be the same for all of them, no matter what orbital transition you're looking at. All right. And then I very quickly surmise that these graphs qualitatively look like a Gaussian distribution. So that's how uh, I inferred that alpha that was shown in the band gap law was 1 over the Boltzmann constant times temperature. Okay, so to wrap things up, uh, these are the things I concluded. Um, Doping definitely improves the nanowires of charge transfer. My results definitely make that very clear. We see that the band gap is inversely proportional to temperature. One thing to note is that in the future, uh, researchers should look at the transitions between orbital superpositions. So when I showed the figures with my orbitals, they were all localized near the dopants. Um, that result is probably not going to apply when we're looking at transitions between orbital superpositions. All right. So that's one thing to look at in the future. And then another thing I concluded was that the band gap law only applies to electrons at higher temperatures. There seems to be a limited applicability to electron holes, as my results show. And then another thing I want to point out is that my electron and my electron hole relaxation rates change at the same temperature rate. All right, and that rate is independent of no matter of orbital transition. So no matter what orbital transition you're looking at, the rate of change with respect to temperature is going to be the same for all of those transitions. Okay. And just a quick remark. How's my research going to impact industry? Okay. Um, in, in the past, researchers have had to perform experiments to find the relaxation rates of these nanowires, and they would take a lot of time and effort. So if I can show that this band gap law applies to relaxation rates in even a limited number of cases, it can save researchers a lot of time and effort in those specific cases, and they can just compute the relaxation rates using the band gap law. And that concludes my talk. Thank you very much. Any questions?
Thank you, Kevin. That was great. Thanks for being a guinea pig for our first online talk. Yeah, let's open up for questions if any questions people might have. Yes, Khan.
Right. So my question is about the band gap. Are your calculations sensitive to the value of the band gap? Now I raise this issue because certainly the band gap value that obtained in your calculation is wrong because you did not include spin-orbit interaction. So without spin-orbit interaction, you significantly overestimate the band gap. Now, if you include spin-orbit interaction, which you should do because spin-orbit effect is very, very strong electrically, right? In that case, your band gap value is going to be underestimated, right? So it depends on how you do the calculation. Almost all the time, you're going to get the band gap value wrong, right? And that is fine. That is well known, right? So again, my question is, are your conclusions sensitive to the value of the band gap?
All my conclusions are sensitive to the value of the band gap. Um, I would say yes, definitely. As a part of my research, I looked at the systems of density of states and absorption spectra, and they're very sensitive to the band gap. So 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 yeah, I would say that my researchers is at least somewhat sensitive to the band gap. Any other questions?
Hey, Kevin.
Yeah, hello.
Yes, Braden.
Yeah, I got a question after seeing your energy band diagram. So I'm just wondering, how did you prepare your model to run molecular dynamics at 1000 Kelvin temperature? Because initially it shows that band gap is very wide, wide open, and it's closed after like couple of femtoseconds. So how did you prepare your initial geometry, initial model system?
Okay. So in molecular dynamics, I initially heated it to 1000 degrees Kelvin for my molecular dynamics.
Um, okay, then why initial is band gap almost 1 electron volt open band gap, and then it's completely closed after like 200 femtosecond.
Um, I'm not 100% sure about the reason at this point, but I have some initial guesses, and this is my guess. So I'm not sure if it's right or not. I have to discuss it with my colleagues. So I know. So in initial temperatures, there's almost no energy for that electron. All right, so the electron has less energy at lower temperatures. All right, but then as the temperature increases, the electron gets higher energy, so it can reach more orbitals. And what I'm saying is corroborated by these red field tensors. So at 300 Kelvin, you see that the rates are the transition rates are very low for orbitals near the band gap. However, as the temperature increases, we see that the transition rates for those orbitals subsequently goes up. So my best educated guess is that as the energy increases, the electron gets more energy. That's my best guess. But yeah, I have to into it more and discuss this finding with my colleagues.
Okay, thank you.
I had a similar question. Just to get initial state. So the initial state, is that like the 0 Kelvin lattice that you use?
So I'm sorry, can you repeat your question? I didn't hear.
So when you start your simulation, you have to have some kind of initial positions for your atoms, right? Mm-hmm. Is that taken from some kind of 0 Kelvin equilibrium lattice structure?
I'm not 100% sure. I have to double check on this, but yeah, I do believe that they were started at 0 Kelvin.
Okay, so they're really, at that point, it's of course reasonable that they might change their atomic, I mean, the lattice structure at those high temperatures.
Right. The lattice structure, I mean, should change at those higher temperatures, I believe.
Mm-hmm. But there was one thing that I noticed is that at very early times, so presumably you start them all off at exactly the same initial condition, right?
Yes.
But the band gaps are not the same, right? At early times.
The band gap.
Mm-hmm.
You mean for this figure at 100 degrees Kelvin? I mean 1,000 degrees Kelvin.
Yeah, but I mean at time 0, the band gaps of the different systems at different temperatures are different, right?
Yeah.
So what's the reason that of that temperature dependence of the band gap?
Again, I'm not 100% sure why the temperature depends on the band gap. So the best guess, the best educated guess I can make is that at higher temperatures, the electron somehow acquires more energy, and then that band gap closes. Did you or anyone else have any other questions? Yes. By the way, I can't see your hand, so just feel free to speak up.
Yeah, I thought a smaller comment. I mean, the research you're doing is very interesting. You know, that electron relaxation rates, etc. I think it's interesting in the field of thermoelectric. Are you thinking about applying the method to a similar system? Because I can see a lot of potential issues with the system you are working with. Lateral array is not easy to deal with. You know, with spin-orbit interaction, you know, and then you had the nanowire, which, you know, your results and conclusion may be sensitive to the size and the shape of the nanowire. So a lot of factors going to play a role in here. So I'm wondering if you want to apply your methods to a simple bulk system. You're thinking about just bulk silicon or a simple semiconductor. I would just first to test the methods to be sure that everything is working properly before you apply to a very complex system like lead telluride nanowire.
So you're saying I should apply the band gap law to simple metals, just to ensure that they fit with those simple systems, and then when I make sure they do, then you're saying that I should try and see if I can apply this to lead telluride. Is that what you're saying?
Yeah, I mean, what I meant was, you know, apply it to a similar system. Let's say silicon, germanium, or something something similar again, like telluride nanowire. Because, as I said, I see a lot of issue with doing, you know, calculation with lead telluride nanowire, right? Because it depends on how you design the calculation, how you design the nanowire. The outcomes can be very different.
All right, I understand. I will definitely keep that in mind.
Yeah.
Any other questions?
Anyone else? So if there are no other questions, then I think we should thank Kevin again, even though he can't hear our applause. It's a very nice talk. Thanks again for volunteering for this first, well, you were, I guess, volunteered by NDSU in the closure to this, yay.
All right.
Very good.
Thanks again for having me, everyone.
Yes. That sounds good. And I guess Kevin will stick around for a couple of